Hi everyone, I'm Marius. Welcome to my very first YouTube video. Today I want to present a fun hack which involves networking hardware, electronics and physics. Ever wondered if you could measure the speed of light at home? Or build a very crude fiber optical gyroscope with a €4 networking module? We will take an SFP module, a tiny networking transceiver, and repurpose it to measure the speed of light in a fiber, and later turn it into a gyroscope. And by hack, I mean using technology in ways it wasn't originally designed for. So let's grab your favorite drink and enjoy the video. So you may ask yourself now, what's a SFP module? Yeah, it stands for Small Form Factor Pluggable, and it's used in networking equipment like switches and routers, and it basically makes them more modular. You can just exchange this small module without having to replace the whole router. And I'm pretty sure that while you watch this video, the signal will go from the data center to your device through several of these modules. What kind of modules there are? So there is like this fiber-based ones. This one only supports a data rate up to 1.25 gigabit. It supports a fiber up to 20 kilometers, and it operating in at 1310 nanometer, which is like well outside of the spectrum where humans can see it. Then there are also other ones which are copper based, so you just plug in a normal networking cable, but they of course don't support such long ranges. Also there are fiber based ones, newer ones, which are more sophisticated and support like hundreds of gigabit. In addition, there are also different kinds of fiber based SFPs. This one is a dual fiber SFP. Means that there are two fibers connected to each. On one side there is the laser which sends out the signal, and on the other side is a photodiode which receives the signal. This will be the modules we will be looking at today. But there are also other modules where there is a single fiber connected to each, and they work by having both sides use a different wavelength. Like for example, one side will be using 1310 nanometer, and the other one will be using 1550 nanometers, so they can each send signal over the same fiber. Next, I opened one of the SFP modules to see what's inside. So at the top, then the more silver metallic casing, that's the laser diode, and the one next to it is the photodiode. And so the SFP module is mainly consisting of a laser diode, a photodiode which detects the light, an amplifier which boosts the photodiode signal, and a small EEPROM which stores the manufacturing ID, wavelength and power limits. But there is not much else going on there. Like there is not a small CPU which is encoding the signal or something like this. Let's start by describing the setup. So I didn't want to directly solder to the PCB of the SFP module. It's like double-sided, not so nice to get in there. So I bought the correct connector, and I designed a small PCB which basically just brings out the pins we need. And it's actually not many pins. I think like something like 6 pins or something we need. So it's pretty easy to hook up to it. But one thing, like we cannot just apply 3.3 volts to the transmit pin and think that the laser diode will fire. No, unfortunately that's not how it works, because the inputs are AC coupled. This means there is a capacitor in the path and it blocks DC voltage. So in order to fire the diode, we need a pulsed signal. And for this, I'm using the Raspberry Pi Pico 2, but are roughly around more than 330 kilohertz are required so that my modules are reliable firing the laser. So in the whole setup here, I will always be using 500 kilohertz just to be safe. And this is like this is on the lower bound of what these modules can support. Like they can support gigabit connections. We have a 50-meter networking cable, 100-meter networking cable, which I rewinded on a 3D printed spool because for the gyroscope later it's beneficial to have a wider spool, like with a bigger diameter. Then we have an oscilloscope, and else we have these standard networking connectors for fiber optical cables, and we have another one which is just an adapter from the SFP connector to the fibers I have here. So that's the basic setup. And for the 150-meter measurement, I will just put these two cables in series. These cables, like they look really bulky. They're like 3 millimeters wide, but actually the fiber inside is very thin. This is just protective casing because it's networking equipment. So in a real fiber optical gyroscope, of course, you will be using the bare fiber and not like this. This one even cannot, I don't know if you can see it, but it has like it looks like two wires next to each other, 3 millimeter wires, and this is some protection that if you pull on it or you bend it a lot, it's not going to break. But yeah, this is only because it's networking equipment why it has this. The real internal diameter of this single mode fibers where the light is transmitting in is only 9 nanometers, which is roughly like 5 times to 10 times smaller than a human hair. So yeah, it's like really tiny, and it's quite incredible like how cheap they can sell this stuff, which is like so manufactured to so a tight tolerance. If we want to do this setup not with a SFP module, but buy instead like a laser diode and a photodiode, the experiment will be like at least 10 times, probably 20 times the costs than how I do it here. One more thing, there are actually 2 transmit and 2 receive pins on the SFP module, and this is because the signal, one pin needs to be always the opposite of the other one, like the inverted signal. I guess this is for signal integrity purposes. Like if you have the Raspberry Pi Pico 2, this is very easy to do because every PWM channel is actually connected to 2 pins, and we can configure them that they are the inverted signal of that. This is now our first measurement. So I configured the oscilloscope so that on the first channel, on yellow, it's connected to the transmit pin. So basically it's the 500 kilohertz signal we are seeing, which is generated by the Pico 2 and which is inputted into the SFP module. And on the bottom, the blue one, it's channel 2 and it's hooked up to the receiver side of the SFP module. So basically this is what the photodiode receives after the amplification step. Now we see we can I configured the oscilloscope so it measures automatically the time difference between the rising edge on the on channel 1 and channel 2, so on the transmit and receiving side. So let's zoom in a bit. So yeah, here. And we see it says it's 256 nanoseconds. And yeah, like normal light travels around 300 kilometers per second in vacuum, but in glass it's actually about 1/3 slower, so 200 kilometers per second. You have, of course, a bit more delay because there is also this adapter wire in between, and there will be some delay inside the thing. So this basically lines up with the speed of light, how it should be. So I plugged in now the 100 meter fiber, and we can see that the delay is about 502 nanoseconds. So here it is with the 150 meter fiber. It's measuring a delay of 748 nanoseconds, which is roughly the 750 we were expecting. And so we were able to measure the speed of light in a fiber using this setup, which I think is pretty cool. So I reconfigured now the oscilloscope to also show the maximum voltage it's seeing on the channel 2 on the receiving side, and it seems to be around 600 millivolt with the 150 meter cable attached. So now I will add a 10 decibel attenuator. What this basically does, this device, is it lowers the brightness of the laser, and 10 decibel is a lot. So this will be like adding a 20 kilometer, roughly a 20 kilometer long fiber to it. And let's see how the output voltage looks like. So I connected it now, and it's still between 580 and 600 millivolts. So yeah, it's not really lowering the signal strength. And well, this will be very good for the network applications. This will cause problems for our gyroscope setup later. So what's a gyroscope? It's a device which measures angular rotations. So you probably all have one in your smartphone, or actually you have free, like for free access. And it's inside a device called inertial measurement unit, and it's used for indoor navigation, maybe for fitness tracking your step counts, or image stabilizations when you take a photo, and also in different devices, like for example a quadrocopter or VR goggles. They all need these devices, but these are using a different technology called MEMS, which is also like incredible fascinating, but not the topic of this video now. And I highly recommend watching this video.
And these really fine comb features on the side of some of the devices, you can fit several of those onto a single human hair.
I will link in the video description to the full-length video. So our fiber optical gyroscope takes a different approach, and the cool thing is that it's one of the few gyros which don't need any moving parts. Like the normal gyroscope, I guess everybody is thinking of, which is used in, for example, older airplanes. I found this video about one in Mig21. By taking advantage of the Sagnac effect, and it basically works by splitting the laser beam into two beams and then letting them enter a fiber optical spool on both ends. So the light will go around the loops and in the middle interfere with each other. Now the Sagnac effect comes into play, and it's that if the spool is rotated, it takes one side longer than the other to reach the other beam, and this causes the beams to interfere differently, like they are at a different phase. And we can measure this. In our case, we will just measure the amplitude, and the amplitude will be changing if the device is rotating. I think this sounds very unintuitive, but that's actually why I also wanted to make this experiment. Like I think it's really cool to see that you can measure that it takes longer for the light to traverse on one side of the spool, or like in one direction of the spool, just because it's rotating. It's pretty incredible. A professional fog, which is used in aircraft, submarines, spacecraft, is of course much more sensitive than this thing, and also, like I said, much smaller. And here I'm using a cheap fiber which is not polarization compensating. So this means that the light waves are actually not going to cancel out in the resting position, because the light waves are not directly hitting each other. It's actually like three-dimensional and stuff, and so you can clearly see this if I just pinch a bit the fiber, then the measured voltage will rapidly change. There is actually some pedal mechanism with 3 pedals where you can manually adjust the polarization, but I didn't need to do this. Let's get to the fiber-optical gyroscope experiment. So for this we need, in addition, a 2x2 splitter, or also optical coupler called. And what this does is basically, like we hook one side up to the laser of the SFP module, then it will get split into 2 equal beams on this side here, and we connect these sides to both ends of this fiber optical spool I have here, which is 100 meter long. I put it on a 3D printed spool which is about 40 centimeters in diameter, and then so the light goes through the spool, and then it bounces back after interfering with it and comes out the other side. There is one which is not attached yet, and this is the one we will attach to the photodiode. So with our setup we cannot measure the phase like a professional gyroscope. We are instead just measuring the amplitude, and the problem is that we saw before with the experiment with the attenuator that the voltage on the receiving side is not changing. Like we want to measure the voltage drop to detect the rotation. So I tried to hook up the oscilloscope and it did not work. Instead I had to find a way to directly measure how much light the photodiode receives. So I opened up the SFP module and directly soldered to the photodiode. So the problem first was that it has 5 pins, and I didn't expect to see 5 pins on the photodiode. So I just hooked up to all of them and broke them. I did find one signal which changes voltage depending on how strong the received light is. So this is basically exactly what we want. We want to measure the amplitude. So it actually came out like this, but the signal doesn't have the waveform of the pulsing of the 500 kilohertz. It's just a constant voltage. So I think it just is like how much the signal should be amplified or something. But I don't care too much about that because it's exactly what we need. So let's hook up to this. In the next video I will be hooking up a multimeter to the photodiode, and then we can see how the voltage changed when we are turning the chair. I pinch the fiber first to change the polarization so it nearly cancels out. Then I start rotating it, but as you can see, the voltage is going back to nearly zero when I stop the rotation. So at this point I decided that turning it by hand is not enough. We have to be sure that we really have a gyroscope. So if I rotate it automatically with a constant velocity, then the multimeter should approximately show the same value. I mean, there is a small variance because of the setup, like the rotation axis is not in the middle, my spool is not perfectly round. We should see about the same value all the time. So yeah, here I have to be a bit tight-lipped. It's stealth startup, venture capital, NDAs, and so on, because it's like super innovative what I can show here. Is a Arduino Uno R4 with a ESP Wi-Fi module connected to a teeny tiny stepper and a huge gear. Surfing a website which allows you to control the chair via your phone or your laptop. One thing I haven't tried is looking at the diagnostic interface, which is provided over I2C. This interface probably also outputs a signal strength, so maybe we could have avoided opening the case and directly soldering to the photodiode by using this interface, but I'm not sure how accurate it is and how high the refresh rate is. But somebody else could experiment with that. I hope you enjoyed this video. Please subscribe to my channel and hit the like button. And if you have any ideas what one could do with the SFP modules, please share in the comments. I hope this video encourages other people to come up with cool uses of these cheap modules. Looking forward to your feedback. See you next time.